Hello and welcome to this session on event-driven architecture. How hard could it be? I'll take you through the following agenda. We'll first do some introductions where I'll walk you through event-driven architecture at a higher level. And we'll do that for the purpose of walking down from that high-level picture to a technique that we need in order for any event-driven architecture to work, namely the way we can reliably exchange events. We'll then talk about two techniques on how to do that. We'll walk through outbox pattern, write-ahead lock, change data capture, and we'll then do a notable mention of a higher level architecture design, namely headless data architecture. So to start us off, there is a business flow that we will be mentioning throughout the talk, and it's your standard one business flow where we have a store where we create orders. From orders, we update inventory. From updating inventory, we deliver an order that's suddenly made to our store. And of course, in the modern days, those three boxes are essentially independent systems. They can go through various types of failures independent to each other. And what we want, of course, is we want this business flow to work correctly. And we want to have consistency between all of those components. What will be assumed throughout the talk is that we're mostly interested in those components working in distributed fashion, so as distributed systems, in order to have scalability that we always want to have. So, event-driven architecture at a higher level, and this is on the basis of a great book, Fundamentals of Software Architecture and Engineering View, which I highly recommend, and not only for the purpose of this subject, but also others. Event-driven architecture can come in two flavors. One is with a broker topology, where we have event channels and event processors. Event processors are aware of the topology in the sense that they have information about where to route a given event from the starting event processor. And so as you see depicted here, we are starting with an initiating event, and that event is funneled through event channels in order to hit various event processors. Those event processors have some sort of functionality, and within them they have components that essentially hold state. The purpose of the event processor is to consume an event and to produce potentially a further event that is channeled to downstream event processors. That's your broker topology. Again, components are those parts of the system that hold state. Event channels are those that are responsible for transmitting events between event processors. A different way of looking at an event-driven architecture is a mediator topology. In a mediator topology, we're starting again with the initiating event, but this event goes through an event queue. From that event queue, there is one single consumer, which is the event mediator. And the event mediator's responsibility is to coordinate execution of a given event throughout its business process, passing it appropriately to event processors through their own event channels again. So we see that in this case, event processors can be unaware of the topology, but there's a lot of responsibility that lies on the mediator, because it's the responsibility of this component to appropriately implement the business flow. To look at an example of a broker topology, we can purchase a book in our store. I'm sorry, there's a pop-up here. The question is, can I have headphones? Unfortunately, I don't have any with me. Am I audible? Is that I'm aware that the quality could be better, but the thing is, can you guys hear me okay? We did some tests before the presentation and it seemed fine. Anyway, I'll carry on. I would be great if people can give me some thumbs up on whether they can hear okay. Waiting for some feedback here. Okay, so to continue, using a broker topology, we can go through a simple example. Okay, let's continue then. We'll go through the following example. We're purchasing a book. This initiating event is put into a channel as a place order event. That event goes to our order payment component, which consumes the place order event and produces an order created event, which is then transmitted into two different event processors, one dealing with payments, one dealing with inventory, and we all know what those do. Inventory creates an inventory updated event that essentially is responsible for communicating to the warehouse that there is a resupply needed. And the payment event processor issues two events, one in the case of payment denied, one in the case of payment successful. If the payment is successful, then we fulfill the order and we ship. On the other hand, we just communicate. And in appropriate cases, we of course inform the notification event processor that there's some communication in form of an email that can be sent out. I hope that's all. And that's all clear and fairly simple at this stage. What is our fundamental problem? Again, we need to have a way of updating a component and updating the event channel. And of course, those two actions need to happen either both or none of them in case of a failure. So we need to have consistency between modifying a component and issuing the event to an event channel. This used to be a fairly simple task in a single node systems environment. For the purpose of that, we have been using the two-phase commit. In the two-phase commit, two systems are integrated via a coordinator, which in our case can communicate between storage and our event queue or our event channel, and essentially ask, are those two components, or many in other cases, essentially, is everyone ready to commit? And if everyone confirms yes, then there is a signal to commit. And this used to work great. And essentially, we could make sure that either everyone commits or no one commits if there is a failure. Again, this used to be simple in a single node system environment. It's more difficult in distributed ones because if you look at distributed databases or distributed message brokers, so on the database side, we can talk database, MongoDB, DynamoDB, different databases that come to mind that are no longer single node ones. And of course, on the message broker side, this is Kafka, Google PubSub. We essentially don't have a two-phase commit protocol implemented for those technologies. And this is the harsh reality of distributed systems, that we no longer have that, either between two storage technologies or between storage and messaging technology. And it's not because people are mean or because there's some laziness in the industry. Essentially, this is a fairly difficult problem to solve in a distributed environment. In case of single node systems, the coordinator was basically implemented using a flat file that would write down transactions that are to be made and coordinated. That single node architecture, translated into a distributed environment, introduces a single point of failure because we need some single node that persists to a file. If that node goes down, our system is not operational, and that's of course the main thing that distributed systems are there to eliminate, so that we don't have a single point that takes down the entire database or the entire messaging system. And so this is a reality we need to deal with. We don't have anything that will help us coordinate commits between storage and messaging, and it needs to happen regardless. We can boil this down to a very simple picture. We have our two services and given to where on one hand side we have the order service, on the other hand there's the inventory, and there is a message broker in between. Of course, on the right hand side we could have many consumers of a single message. And essentially here's our problem, right? There's a database, order database in this example, a change needs to go there, and likewise a change needs to go into our message broker. And either both happen or none of them happen at once. Let's look at some simple options on how we could do that. Maybe if our message broker of choice is Kafka, we could have two communication topics. We can have two topics, right? Communication topic and a persistence topic. We know we can have transaction between those two. And we could use communication topic to essentially inform downstream that something happened. And we could use persistence topic in order to push something to our database. That's consistent, but that eliminates a very important property of order service. It no longer has read after write semantics. We essentially persist something, our write event or write request comes back as successful, but we don't know if the thing is in our database already or not, which makes the logic of order service very difficult to implement. And so the problem is not trivial, right? This is why people come out with solutions on how to do that. We'll now walk through three categories of those that are widely discussed. And my goal is to shed some light on them and essentially communicate the simple message that it's never trivial, and we always need to worry about something in the case of those patterns. So first off is an outbox pattern. In the outbox pattern, what we do is we assume that in our database we have our data table, in this case the order table, and we have a special outbox table, and that is a twin table to the data one. And the sole purpose of the outbox table is to persist notifications that something happened in the order service. And so we have a transaction between the order table and the outbox table, obviously. That's simple. Fair enough. What happens next? We want to read outbox table using a message publisher, and we want to publish those notifications persisted in the outbox table to the message broker. What could go wrong? Indexing of the outbox table isn't trivial. We essentially need to index a flag that says that something was already exported or not. And if we're indexing a boolean, this means that our index can be low performant essentially. There are techniques to deal with that. Some databases offer no filtered indices, but essentially we face this problem that if there is a write heap to our system, we can end up with many records that haven't been published yet. If that's the case, then it might be difficult to read all of those records into our message publisher and process them. And B, it might be difficult to update our outbox table because we might end up with too large transactions. Of course, some batching technique could help us with the problem. But if we're doing that, then it is more difficult for us to make sure that, for example, we fulfill any ordering guarantees if we have such a requirement, and often we do, right? We want to stream out changes in the same order in which they happened in our original database. And that's not trivial if our queries essentially pull in some random subsets of the outbox table and stream out those notifications to the message broker. What might also be difficult is just the orchestration, right? If we have many data tables, we have many outbox tables, and for all of them we need our message publishers to work. Batching needs to, if it's there, needs to work correctly in all of those cases. So it's a way to solve the problem. It's one of those ways where we need to be prepared for difficulties when you operate a solution using index pattern. Another approach is a write-ahead log. In a write-ahead log, what we essentially assume is that we're persisting our change to an internal order service topic, and after that we persist it to a database. And that's why write-ahead log, right? We first persist something into a log that is in our message broker. What needs to happen after that? We need to, of course, rewrite our notification for our log event from the internal topic to the communications topic. What we need to do in between is we need to somehow hack in our database that a given order was already processed by the internal topic. And why we need to do that? And that's because we essentially can have a failure between 1 and 2, right? And this alludes to the failure modes point that is listed below here. In a scenario where we persist something into the internal topic, but our database transaction fails, we end up with a record in the message broker that is an orphaned record in a way. And if our client doesn't retry, then we essentially end up with this orphaned record and we need to filter it out because it doesn't exist in the database, right? So in order for this integration pattern to operate correctly, we rely heavily on our clients retrying any failed writes that happen to our order service. We again lose our read after write semantics, right? Because immediately after 1 and 2 are executed, we, yes, have the record in our order database, but we're not sure if our message broker correctly emitted notification to downstream, right? And in some cases we might not care about that. In some cases, which is the better option. In some cases, we might, in which case, we need to again play with some sort of a published or non-published flag. And we'll see in a second slide how we can deal with that. Of course, there's an impact to the write latency because we're now performing two operations and to two independent systems when our write request is executed. How we can improve this integration pattern? There's a variant that I want to walk you through. It's one where we again have a write latency because we're modifying two systems. And we're using an experimental feature that is present there in Spring Kafka in the correlation IDs used for synchronous communication using Kafka message broker. But there's an interesting solution that we can design using this feature that eliminates some of the problems that we've been discussing. How does it work? We have our client on the left-hand side, And we have our order service. This order service, as mentioned, communicates with the order database and with Kafka message broker. And we have an order notification service that is essentially part of the order service. The order service's responsibility is to perform the write. It's the one that interfaces the client. And the order notification service is an internal service that deals with Kafka communication, also some internal database communication, and notification rewriting. So let's see what happens. We have our client that places an order. As soon as this happens, we're persisting data to our order service database, and we use this published equal false flag, which means that this record isn't yet fully persisted, so to say. We have an act that comes back. We have successfully completed the initial transaction, and we then do a special operation that Spring Kafka allows us to do, which is send and receive. And we send and receive an internal notification. When we do this, the internal notification comes out with a special correlation ID that allows us to then tie back this notification to a response that comes back through a different Kafka topic to which the Kafka producer is listening in the background. When we do send and receive, what happens with the thread that handles our write request, our place order request, is that it hangs. It essentially hangs, and this is what is depicted here. While it hangs, our notification service reads the internal notification via a consumer group, and on the back of this read, it updates our published flag to true, indicating that this record now has a representation both in the database and in the message broker. So far, it's very similar to just the standard variant of the write-ahead log. That published equal true transaction comes back successful. And what happens then is 3 operations that we can perform in a single Kafka transaction because they all relate to Kafka topics. What happens is we send out the external notification, we do a response to the initial send and receive message. That response contains the correlation ID, and so we're able to deliver that Kafka message to the thread that is hanging here and waiting for the response. And we commit the internal notification topic offset to indicate that we've now completed processing of the internal notification. What happens is 2 things. One is we're unblocking the producer, so the writer thread which now can return to our client and communicate that the order was placed successfully. And independently, of course, we have our external notification on a separate Kafka topic, which then can be read using a different consumer group, of course, by a downstream consumer, namely inventory service in our example. What have we achieved here? We essentially achieved the synchronous communication between client and order service. That is capable of ensuring that a change either happened to both database with the published equal true flag and a Kafka message broker. What is tricky about this approach, again, failure modes are slightly simpler than in the previous examples because as long as this transaction succeeds and we're able to persist a notification to a Kafka topic, we are now in a situation where we drive all of the further processing off of a message that exists on a broker. And so repeating of that processing in case of failures is fairly trivial. We of course can be in a situation where, hey, this processing here takes time, and so we have a timeout that happens here. In that case, we need to communicate that timeout to our client, and we need to have some sort of API that allows them to check if a given write request now became successful or not. That complicates client logic a bit, but again, it's a failure mode that we're dealing with, right? So hopefully we don't execute that failure mode path too often. Of course, what can happen as well is that we can persist a record to the database, but fail to persist to the message broker here at the beginning. But if that happens, we have a record that is invisible to our client because it has this publish equal to false flag. And we've communicated the failure to the client, so we can either ignore if client doesn't retry, and on retry we can continue with the processing. What of course this means again is that if the client doesn't retry, we end up with an orphaned record in the database, right? It's thankfully invisible thanks to the flag. We might have some sort of a process that continuously goes through the database and removes those unretried records after some sufficiently long period of time. That's not simple, right? Just to say the least, but we're at least solving some problems that we saw with the earlier patterns. We'll now move on to something that is simpler, and this is a change data capture pattern, where we essentially say that we're making the whole thing a databases problem. What happens in the change data capture is that we're essentially tailing the transaction log of the database. And we have some sort of record change replicator that listens to the transaction log, and it replicates transactions to a topic, to a Kafka topic, to a PubSub topic, whatever technology we use for streaming out changes. What needs to happen is we need to have some sort of a transform, because essentially what the record chain replicator does is it replicates the transaction information, which is quite raw and needs to be transformed into a business understood event. And this is why we still have two topics, one in the internal one and one communication for consumption by the downstream. Fairly simple. And modern databases, by and large, implement this possibility to hook in a change data capture component. You might be aware of the project Apache DBZine, which essentially has the goal of providing an ecosystem in which it is fairly simple to hook in those components, those message replicators, into an existing system architecture. It's not a rose without thorns, but those thorns are fairly small compared to the previous ones. We essentially need to control the load that the replicator puts on the database, right? And it is load that is additional to the load that our production traffic puts on the database. And that's important to remember. We need to have sufficient resources on the machine that hosts the database, well, the machines, because we're again discussing distributed databases here. And again, modern databases essentially have that implemented. We then need to also manage the replicator progress, right? We need to be aware of how far behind a given replicator is in any given case. Yes, because of course, if the record change replicator is not capable of keeping up with our production volume, then there is a delay in which we send out our notifications to downstream, which essentially is a fairly intuitive problem to have. And in this case, of course, we're not modifying the database and the message broker synchronously, but we do that reliably. And so we have this eventual consistency between the database and the message broker. Okay, we're done with the methods for consistent modifications of the database and the message broker that I wanted to present to you. There's a notable mention about headless data architecture, which is an architecture proposed by Confluent, the company behind Kafka. So it's important to mention how does this relates to what we've been talking about previously. And in this architecture, what is assumed is that we have a source system again that produces some data using some creation logic. This data is then put on a Kafka topic, it then can be transformed. After transformation, it can be put into an iceberg table. And of course, after we're done with all those 4 steps, we can use this data for various different use cases, stemming from SQL queries to real-time application, to analytics, to machine learning and AI, etc. How does this relate to what we've been talking about previously? And does this solve our problem in a way? Not really, because what this doesn't mention is how do we maintain consistency between our source system and our Kafka topic, right? There is no coordination between the source system and the topic that is mentioned here. And so again, what we've been mentioning is how essentially we can implement point 1 of this architecture. The subject is discussed widely in the internet. There are some links here that you can use if you want to read more. There are 2 books that I recommend that mention the topic. They're great not only for the subject specifically, but for others as well. And that's Designing Data-Intensive Applications and Fundamentals of Software Architecture. With that, thank you very much for your attention, and I'll take any questions that you may have. Okay, we have a question. How to move to an architecture that is based on events. Przeczytam po polsku. W jaki sposób przejście na architekturę opartą na zdarzeniach komplikuje zarządzanie transakcjami w systemach rozproszonych? No, szczęśliwie w systemach rozproszonych transakcje, pytanie, o czym dokładnie mówimy, czy o technologii takiej jak rozproszona baza danych, czy o rozproszonej architekturze. Jeżeli mówimy o rozproszonych bazach danych, czy rozproszonych brokerach wiadomości, to nie mamy komplikacji, tak? To są technologie, które zarządzają naszymi zdarzeniami. W rozproszonej architekturze, no właśnie, jeżeli chcemy przejść na architekturę zdarzeniową, to musimy rozwiązać ten fundamentalny problem, w jaki sposób nasze zdarzenia zmieniają równocześnie bazę danych i nasz event streaming. Jeżeli to rozwiążemy poprawnie, to komplikacje nie są duże. Jesteśmy w stanie operować. Oczywiście jest to system bardziej złożony niż taki, który działa na pojedynczych węzłach, ale jest również bardziej skalowalny. Potrafi obsłużyć większy wolumen danych, więc jest czymś dla nas pożądanym. Mam nadzieję, że to odpowiada na pytanie. Kiedy mówimy o architekturze opartej na zdarzeniach, jak najefektywniej projektować reakcje usług na różnorodne zdarzenia? Projektować reakcje usług na różnorodne zdarzenia. To zależy od tego, jaką konkretnie mamy architekturę opartą na zdarzeniach. Czy bardziej mówimy o tej architekturze brokerowej, czy bardziej o tej z mediatorem. Tak? jedno z tych podejść musimy wybrać. Albo mamy koordynatora, który wie, w jaki sposób reagować na różne zdarzenia i robi pewną taką orkiestrację, która za nas się dzieje, czy jest dla nas wydajniej, żeby i jakoś lepiej, żeby te reakcje na zdarzenia były powiedzmy, zahardkodowane w naszych event procesorach, tak? Czyli w poszczególnych komponentach, które przetwarzają zdarzenia. I jeżeli tak, no to jest to pewna logika, którą musimy zaimplementować w event procesorach. I jest więcej o tym w tej książce Fundamentals of Software Architecture, także też odsyłam do niej w tym temacie. Czy mamy jeszcze jakieś pytania? Mam tu informację, że to jest ostatnia chwila, więc pytajcie. Dziękuję bardzo za uwagę. Nie ma więcej pytań. Bardzo dziękuję i zachęcam do przeczytania więcej informacji.